Hello everybody. Today we're going to be talking about our first lesson in Chapter 9, which has to do with scatter plots. Chapter 9 has to do with statistics and probability. So one of the first things we want to look at in terms of statistics is a scatter plot. So when we have data that has two variables or pairs of numerical observations, we call that bivariate data. Basically what we're doing is we're taking a look at two different things and we're comparing them against one another to see what type of relationship exists between them, if any. Okay, so a scatter plot can show the relationship between the bivariate data graphed as ordered pairs on a coordinate plane. For example, the bivariate data set year and the number of visitors can be displayed as a scatter plot. So we want to see if there is a relationship between the number of visitors, let's say to a theme park, and the year. This way we can see, are we getting more visitors per year? Are we getting less visitors per year? Is it up and down? Is it pretty flat? This gives us a big picture of our data, what the data is doing in general. So if we take a look here at example number 1, it says construct a scatter plot of the number of viewers who watched new seasons of a certain television show. So what we can do is we want to put the seasons on the bottom, on the X, and the viewers on the Y. And all we're going to do is graph these ordered pairs. So down here, again, when we make a scatter plot, it's very important to label. Down here is season. Over on the side is viewers. And again, millions. So let's take a look here. At 1, it's 31.7. Now, obviously, 31.7 isn't going to fit on here, so maybe I want to go by 5s. So that gives my graph here. Seasons, of course, I can go by 1s, and I can just label that. Like that. So season 1 we had 31.7 viewers, so that's just over 30, about right there. And season 2 we had 26, just over 25. Season 3 we had exactly 25. Season 4, 24.7, pretty close to 25. 5 we dropped down to 22.6. and 6, 22.1. So here is our scatter plot. This gives us a big picture of our data. What is it doing? It looks to me as though it's going down and then kind of flatlining a little bit. So we can clearly see by looking at it immediately that over the time of the show the viewership is going down. And that's really the power of a scatter plot, is that I can instantly know what the data is doing just by looking at it. I don't have to examine the numbers and think, okay, it's going down a little bit, keep going down, keep going down. I can instantly see it. It is a snapshot of our data and what it is doing. So go ahead and pause the video and try A under the Got It section on your own, and I will be back in a minute to go through that with you. Okay, we should be back from trying A on our own. So we have weeks and weight in pounds, and this is the weight of an alligator after it hatches. So weeks we'll put down here on the bottom, and weight on the y-axis. Okay, so at 0 weeks the thing weighed 6 pounds. So here's 0, here's 6. At 9 weeks, it weighed 8.6 pounds. So now notice I can't get exactly to 9 and I can't get exactly to 8.6, so I'm estimating. Here's about 9, 8.6 is about right there. At 18 weeks, he weighed 10 pounds. Here's 18 weeks, roughly 10 pounds. 27 and 13.6. Right in there. 34 and 15. 34, 15. 43 and 17.2 would be about right in there somewhere. And 49 and 19.8 right up there in that corner. Okay, so clearly we can see, I'll make these a little bit bigger. Clearly we can see that our data is going up. As the alligator gets older, he's going to continue to gain weight. Okay. However, I do believe at a certain point that should probably taper off. Okay. Once you reach adulthood, you tend to stop gaining weight at the same rate that you did when you were a child. Okay. Now, the next thing is we want to categorize our scatter plots into different types of associations that we can see. So the first one is what we call a variable association. What is the association between the variables? Okay, we can have a positive association. So as x increases, y increases. The graph will be going up. That's a positive association. We can have a negative association. So as x increases, y decreases. Our graph will look like it's going down. Or we can have no association, where it is just all over everywhere and there is, like it says, no obvious pattern. Okay, so that's the first type of association we look for. The next type is going to be linear or non. Okay, so linear, again, remember, means line. If it looks like you can draw a line through it, or it's in a relatively straight pattern, okay, we're going to call that a linear association. Okay, if it's not, okay, this one looks like we would call that nonlinear. So here you can think this kind of approximates, that's a straight line. Our data here looks more like this. That would be nonlinear. Okay, so if it can be approximated using a straight line, we're going to call that a linear association. And if it can't, it'll be a nonlinear association. So the two types of association work in tandem. You can have a positive linear association, you can have a positive nonlinear association, you can have a negative linear association, you can have a negative nonlinear association. If you have no association at all, it will not be linear or nonlinear. So if it's no association, that's what it is, no association. That we can't tell if it would be linear or nonlinear because there is no association. The other things we look for are called outliers and clusters. Okay, and the names kind of give away what they are. So it says you can analyze the shape of the distribution of a scatter plot to investigate patterns of association. If the distribution shows a positive or negative association, then the distribution can be classified as linear or nonlinear. I already talked about that. The scatter plot below shows a positive nonlinear association. Clusters or outliers can also be identified. So an outlier is one outlying by itself. Okay, one that is way far away from anything else. That is what we would consider to be an outlier. A cluster is a collection of points that are close together. So if you have a lot of data points that are right on top of each other, that is considered a cluster. Okay, so a big cluster of points is a cluster. One out by itself is an outlier. These are usually pretty easy to spot. Okay, and the names pretty much tell you what they are. So here we have a scatter plot. Take a look at example number 2. It says interpret the scatter plot of the data for the amount of memory in an MP3 player and the cost based on the shape of the distribution. Okay. So when it says interpret the scatter plot, what I want to know is there any type of association, okay, positive, negative, none. If it's positive or negative, is it linear or nonlinear? And then, are there any clusters or outliers? Okay. So when I look at this one, to me, this looks like a positive linear association. Okay. They're all kind of going in a straight line here. So I would say positive linear association. Okay, positive linear association. The next thing we would look for would then be any clusters or outliers. So if we want to take a look at where a lot of our points are, I think there's a cluster right here between 1 and 2 gigabytes. Right here. Look at that. There's 1, 2, 3, 4, 5, 6, 7, 8 points. Almost half of our data is right there between 1 and 2. So you can say a cluster between 1 and 2 gigabytes. Oops. Should be a B. Gigabytes. Okay, cluster between 1 and 2 gigabytes. And lastly, an outlier. This one is way off the radar. I would consider that one to be an outlier. Outlier at, and we can just name the point 8, 200. Okay, 8, 200. So to effectively interpret a scatter plot, you want to tell me the variable association, you want to tell me the linear association, and identify any clusters or outliers. Okay. So go ahead and try B and C on your own under the Got It section. I'll be back in a minute to go through those with you. Okay, we should be back from trying B and C. Let's take a look at B. So it says interpret the scatter plot of the data for the time elapsed and temperature of water based on the shape of the distribution. So here it looks like we have some water that is cooling down. Okay, this to me is a linear association. Okay, follows a pretty straight path down. Since it's going down as x increases, y decreases, this would be a negative linear association. Okay, I don't really see any clusters. It looks pretty standard. So no clusters, and yes, you do have to write no clusters. And I also don't really see any outliers. So here I've addressed all of the questions necessary for interpreting a scatter plot. Negative linear association, no clusters, no outliers. If we take a look at C, here we are talking about the days and the number of pints sold for an ice cream shop. I look at this and I see no association. So if it has no association, I can't tell if it's linear or nonlinear, so I don't need to worry about that. Here, you know, I don't really see any clusters. Maybe you could consider this an outlier, but it's really no further away from the rest of them than these ones up here. So I would go no outliers as well. No association, no clusters, no outliers. Our data is just all over the map. Okay? It's just all over the map. So take a look at example number 3. It says, the table shows public school enrollment from 1999 to 2010. Construct and interpret a scatter plot of the data. If an association exists, make a conjecture about the number of students that will be enrolled in public schools in the year 2015. So a conjecture is a statement or a guess based on the information that we have. So here we're going to combine the last two examples and we're going to make a scatter plot, then interpret it, and then we're going to make a guess, and we're going to use this to predict the future essentially, or take a good guess at it. Okay, the power of statistics is that we can take all of the data that we've been collecting for years and years and years and use that to see or to shape our guess of what's going to happen in the future. And so many industries are based on this. It's just really, I don't know, super useful. Okay, so let's see here. I've got my graph on the other page. So if we look at our data, we have years since 1999, 0 through 11. So I'm going to put that on my x-axis, and I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I can just make one more out here, and we'll call it 11, so we'll go by ones. On the other side, if you look at our data here, it is really let me show you here. It's really tight between 46.9 and 50. So one of the things we don't want to do is we don't want to make a broken graph. Sometimes you'll see a little zigzag mark that kind of looks like this, okay, at the bottom of a graph, and then they'll just skip right to 40. That is one of the ways you can skew statistics, because then the difference here, if you look at it, it looks like our numbers are going up a lot. Your graph will be more up and down. Okay, but really, in actuality, if you have a decent graph, it's not. It's pretty flat because it's not really going up a whole lot. Okay, so we want to avoid a broken graph, but our numbers are primarily between 46 and 50. You know, so if we go by fives, which everything's going to be right up here at the top. If we go by tens, it's going to be all pretty well crowded and you won't be able to tell much. So maybe we try to go by fives. So 5, 10, 15, 20, 25, 30, 35, 40, 45, and 50. So all of our data is really going to be right up here at the top. Okay, so in year 1 we're at 46.9, which is just over 45. At year 2 we are at 47.2, 47.7, 48.2, 48.5, 48.8, 49.1, 49.3, 49.3, 49.6, 49.8, and finally 50. So here, when we look at this graph and a non-broken graph, it's really flat. Okay, this doesn't look like much change at all. However, if I were to do something like this, where I had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and let's go 1, 2, 3, 4. Okay, where I started at 46 and 46.5, 47, 47.5, 48, 49 or 48.5, 49, 49.5, 50, and that would be it. Then when I plot these on here, and I'm not going to take the time to go through them, it looks more like this. Okay, so you can see here on this broken graph down here, now it looks like, wow, the number of students is skyrocketing. However, that's a broken graph. Okay, it's not showing you the whole picture. When we take a look at the whole picture, this is what it looks like. Not real exciting. Okay, so you can see why companies will try to do that, but really they're skewing statistics. And if you don't understand that, you can be duped by corporations or the government or anybody else trying to peddle bad statistics on you. Okay, so it's important that we understand the construct of a graph and why a broken graph doesn't necessarily tell the whole story. Okay, but anyway, back to our problem here. It says interpret the graph. This obviously is going to be a slight positive association, and it's going to be linear. I mean, look at it, it's almost essentially a straight line. So we'd say positive linear association, no clusters, no outliers. Okay, so that's my interpretation. I've interpreted the scatter plot. Now, I don't know if you guys can see that. Okay, now I need to make a conjecture about how many students will be enrolled in public schools in 2015. So what we have here is the year since 1999. 11 years since 1999 would be 2010. Okay, so you can see from these last 5 years it went from 49.1 to 50. In the first 5 years it went from 46.9 to 48, so it almost went up 2 million students there. Here it only went up about 1. Okay, so if the current trend continues, okay, of going up 1 million students every 5 years, in 2015 we could say there would probably be 51 million students. In 2015 there will be 51 million students in public school. Okay, so that's your conjecture. The guess about what's going to happen, that is the conjecture. Okay, and I know it's kind of hard to see on here because I had the 2 pages. But here was our data. This is our conjecture. In 2015 there will be 51 million students in public school. And then here was our graph. And again, don't use the broken graph. That's bad statistics that misleads people. Use the real graph. This is really what's going on. Pretty stagnant, slow growth. Not this. Okay? This is what you do if you want to buy a new school or you want to build a new school. Look at all these kids coming. This is ridiculous. We need a school. Okay? This is what you do if you don't want to build a school. Nobody's coming. Okay? So, go ahead and pause the video and try D on your own, please. I'll be back in a minute to go through it with you. Okay, we should be back from trying D on our own. It says interpret the scatter plot from the men's Olympic 100-meter freestyle. Swim winning times. If an association exists, make a conjecture about winning time in the 2016 Olympics. Okay, so again here, to me this is a pretty linear association, and it's obviously negative because it's going down. So this would be a negative linear association. Okay, no clusters, no outliers. So there's my interpretation. Now I need to make a conjecture about it. If we take a look at our time, it continues to go down. In 2008 it was roughly, looks like 47 seconds. So another 4 years would be 2012 right here, and I would say maybe down to 46 seconds maybe. And then 16 would be this last one right here, and I maybe 45.8, 45.5 would be a decent guess. I mean, if you look at the path, it would kind of end up down there. So I'm going to say in 2016 the winning time will be under 46 seconds. Okay, so this is the power of a scatter plot. It gives me a very clear picture, a very quick picture of what the data is doing, and then it allows me to make a conjecture or a guess about the future based on the past. Okay. So with that, here's the assignment. Go ahead and get started. Choose the assignment that is best for you. If you've done well and you understand everything today, go ahead and do green. If you understood some parts but not all, do the yellow. And if you're struggling, do the red. And as always, have a great day.